Hello students, how are you? I hope you are doing well. Today I have come with questions based on electrostatics and current which were asked in the second shift of 29 January 2023. Okay, so without wasting time, let us discuss them one by one. You can see a point charge 2 into 10 power minus 2 coulomb is moved from P to S in a uniform electric field of 30 Newton per coulomb directed along positive x-axis. If coordinates of P and S are this, the work done by electric field will be. So this is a formula based question, students. Work done by any force, constant force, can be obtained as the dot product between the force and the displacement. So you can apply that concept here. Now you see the force acting on a charged particle is Q into vector E, because electric field is given and charge is also given. So we have this force offered by the or force exerted by the electric field. Now when the charge moves from P to S, the displacement is vector R, which is actually the position vector of final point minus position vector of initial point. And accordingly we can have the work done as the dot product between these two. Okay, so here you have Q into vector E dot vector R2 minus vector R1. So let us substitute the values. Charge is 2 into 10 power minus 2. So 2 into 10 power minus 2. Electric field is 30 I cap because it is along the x-axis. Now R2 minus R1. You know how to calculate the vector joining the any 2 points. Position vector of head minus position vector of tail. Okay. So x2 minus x1 into I cap plus y2 minus y1 into j cap plus z2 minus z1 into k cap. So difference in x coordinates will be minus 1, so into I cap. Difference in z coordinates will be minus 2 into j cap. That's all. Difference of z coordinates is 0. So this will be 2 into 30, that is 60 into 10 power minus 2. I dot minus I is minus 1 and then 0. So finally you have around 0.6 joule. Since the options are in milli, so multiply and divide by 1000. When you divide by 1000, you get milli, and simultaneously when you multiply by 1000, this will be 600. So 600 millijoule with the minus sign. Don't forget to put this minus sign. This minus sign is there. Okay, so minus 600 millijoule is the correct answer. Okay, then what you can do, students, without undergoing all this, simply if you can understand the basics of electric field and the movement of the charge and all, you can very easily calculate this almost immediately. Let us see how to calculate. This is another method. It's up to you whether you like it or not. Okay, now you see the electric field is clearly given as 30 Newton per coulomb along x-axis. Okay, so we are only interested, so work done, okay, force on a charged particle will be in the direction of x-axis only. So we are interested only in the displacement along x-axis, because as you know, work done is given by magnitude of force multiplied by displacement in the direction of force, or the component of displacement in the direction of force. That's what we have. So force is Q into E. Now let us see the displacement along x-axis. See, initially the x coordinate was 1 and then it became 0. So it was moved from 1 to 0. 1 to 0. So initially it was, suppose I take this as x-axis, initially it was at x equal to 1 and then it was moved to x equal to 0. So the displacement is 1 meters to the left. So displacement is 1 meter to the left. So cos 180 will come here, and cos 180 degree is minus 1. So minus QE. Q is how much? Charge is given as 2 into 10 power minus 2. So 2 into 10 to the power minus 2, and electric field is 30. So you have minus 0.6 joule, which is minus 600 millijoule. This also you can calculate. Moving on to the next question. For a charged spherical ball, electrostatic potential inside the ball varies with R as this. Here A and B are constants and R is the distance from the center. The volume charge density inside the ball is this. Okay. So we have to find the lambda. First we have to calculate the volume charge density and then we'll equate that to this to get lambda. Right. Now you see, if you know the formula, students, if you know the formula of potential within a charged sphere and the charge should be symmetrical, okay, this expression corresponds to symmetrical charge distribution only. So if R is the radius of the sphere with a uniform charge distribution, again I am repeating, the charge distribution should be uniform, that is rho should be constant, only then you have this formula whatever I am writing here. So at a distance r smaller from the center, you know potential is k q by 2r cube into 3r square minus small r square. Okay, this formula is very common and I hope you know this. If you don't know, then just note down this formula. Okay, you are supposed to memorize these formulas. So when we open the bracket, we have k cube by 2r cube into minus r square plus 3kq by 2r. So as you can see, we are only interested in the value of volume charge density will come out in terms of A. So if we can know the value of A, then it's done. Okay. So what is A then? A in terms of Q we have to know. As you can see, 2A is the coefficient of R square. Okay. So what is the coefficient of R square? That will be 2A. So 2A will be equal to minus K. K is 1 by 4 pi epsilon 0 into Q upon 2R cube. Sorry. Okay. So this will be Q by 4 pi R cube upon 2 epsilon 0. I have separated 2 epsilon 0 from here. And if I multiply and divide by 3, this will be rho, volume charge density. So rho upon 6 epsilon 0. This is 2A, remember. So therefore, A will be rho upon 12 epsilon 0. Now, the volume charge density they are given as minus lambda A epsilon 0. Don't forget the minus sign, students. Again and again I am forgetting the minus sign. So this rho will be, they have given it as what? Just look there. It is given as minus lambda A epsilon. So minus lambda A epsilon. I have taken epsilon 0, it doesn't matter. So therefore lambda is 12. Okay. Lambda is 12. This one method to know this. Okay. There are other methods also. Okay. We'll take up one more method to know this, to derive this. Alright, students. Now if you know the formula of electric field inside a uniformly distributed charge sphere, then it is rho r by 3 epsilon 0. I hope you know this. Okay, electric field intensity at a point smaller distance away from the center within the solid sphere, uniformly distributed charge. And this will be minus dV by dr because we have to interlink with the potential. So I can write this as dV is equal to minus rho upon 3 epsilon 0 r dr. Now integrating both sides. Initially, when at the center, let us say the potential is V naught, and somewhere at a distance r, let us say the potential is V. So after substituting the limits and all, you get this. V minus V naught is equal to rho upon 3 epsilon 0. After putting the limits, you get this as r square by 2. R square by 2. So therefore, you can very easily see that V is equal to rho upon 6 epsilon 0 into r square plus V naught. So if you compare the thing given, coefficient of r square is 2a. So coefficient of r square is 2a. So this must be 2a. So 2a is equal to, with a minus sign, minus rho by 6 epsilon 0. So therefore rho will be minus 12a epsilon 0, and they have given this as minus lambda a epsilon 0. So lambda is 12. This also you can calculate. Then moving on to the next question. With the help of potentiometer, we can determine the value of EMF of a given cell. True. The sensitivity of the potentiometer is. Now students, sensitivity is, what do we mean by the sensitivity? In fact, sensitivity of any measuring instrument, the basic idea is whatever it is supposed to measure, okay, a small change in that should be reflected very, very clearly and lucidly. That is, there should be clarity, and the instrument should be able to manifest the change clearly. For example, say sensitivity of a thermometer. Thermometer is supposed to measure temperature. Now, if a small temperature fluctuation is manifested in the thermometer nicely and properly, then we'll say that the thermometer has high sensitivity. Similarly, say an ammeter. An ammeter is supposed to measure a current. If a small change in current, okay, is reflected properly on the scale, the needle fluctuates properly, even if the change in current is a very small value, then we say the ammeter has high sensitivity. So this is how we develop the concept of sensitivity of an instrument. Whatever it is about to measure, a small change in that should be manifested and reflected properly in the instrument. So here a potentiometer, as you know, that we go on touching the jockey at different points of the potentiometer wire, okay, and during whatever thing is being balanced there, okay, and we measure the balancing length. So if the potentiometer wire is long, then the potential difference will be spread over a longer length, and it will be more easier for us to find the balancing length. That is, you have more chances to find the correct balancing length if you have a longer length. So sensitivity is high if the length of the potentiometer wire is large. So we can say first is correct. It is directly proportional. Sensitivity is directly proportional to the potentiometer wire. Is correct. Then the second thing is that it's directly proportional to potential gradient. Now if you talk of potential gradient, then potential gradient is the fall in potential per unit length. So if length is more, potential gradient should be less. So E is wrong. So automatically C will be correct. Again, you think in the same terms. Larger the length of the potentiometer wire, better it is. So if large length would indicate low potential gradient. So inversely proportional to potential gradient. So D is wrong, of course. So A and C. A and C means second option is the correct option. Then moving to the next question. We have when two resistances R1 and R2 are connected in series and introduced into the left gap of a meter bridge, and a resistance of 10 ohm is introduced into the right gap, a null point is found at 60 cm from the left side. Okay. Then when R1 and R2 are connected in parallel and introduced into the left gap, a resistance of 3 ohm is introduced into the right gap to get null point at 40 cm from the left hand. The product of R1 and R2 is not very difficult. Okay. There are two situations, students. In the two situations, they have shown that the balancing lengths are different because the resistors in the gap are different. Okay. Now coming to the first case, see the two resistors are joined in series. Let the effective resistance be S, that is placed in the left gap, whereas in the right gap you can see in the right gap has a resistance of 10 ohm. So I'll write it here 10 ohm. And the balancing length is found to be 60 cm from the left end. So this is the left end. So 60 centimeter from the left end means this. So since it's a meter scale, total length of the wire will be how much? 100 cm. So this side has to be 40 cm. So immediately I can write S by 10 is equal to 60 by 40. This is the principle of Wheatstone bridge. So S upon 10 ohm is equal to 60 cm upon 40 cm. After cancelling out, I have this 2 2s and 2 3s, again 2 5s. So S is equal to 15 ohm. So the series combination of R1 and R2 will be having an equivalent resistance of 15 ohm. Next, they have now been connected in parallel. Let us say the equivalent resistance is P, introduced in the left gap, and 3 ohm resistance is introduced in the right gap. This time the balancing length is 40 cm from the left end. So this length is 40 cm. So obviously this will be 100 minus 40, that is 60 cm. So again, if you apply the principle of Wheatstone bridge, we have P upon 3 is equal to 40 by 60. Okay, so 0 0 get cancelled, 3 2s are 2 2s are. So 2 is the parallel. Now we have to find the product. Now as you know, students, when two resistors are connected in parallel, when two resistors are connected in parallel, then the effective resistance will be product upon sum, isn't it? The effective resistance will be product upon sum. This is what is set here. So P, which we got it as 2, is basically product upon sum. And sum is already there because in series the effective resistance will be the sum of the two. So the product will be this 2 into 15, that is 30 ohm square. So product is 30 ohm square, 30 ohm. This is the answer. Moving on to the next question. A null point at 200 cm in potentiometer wire. When cell is in secondary circuit is shunted by 5 ohm. When a resistance of 15 ohm is used for shunting, then the null point moves to 300 cm. The internal resistance of the cell is. This is very simple question, students, but you should know how to solve. So two things are required here. One is the principle of potentiometer wire. That is very simple. The voltage across the balancing length. Okay, whatever be the voltage, it could be due to a cell, it could be due to any voltage source, should be equal to the potential gradient multiplied by the balancing length. So voltage across the potentiometer should be same both ways. So that is the principle of potentiometer wire. So suppose you have a potentiometer wire here, okay, and this is the primary circuit. A voltage is developed across the potentiometer wire so that a main current starts flowing. This is known as primary circuit. Primary circuit. There is a potential difference across the potentiometer wire, okay, and its length is L. So its potential gradient, which is the fall in potential per unit length as we move from A to B, is constant as long as we don't disturb this primary circuit. And in fact, as you will realize that in most of the cases, the primary circuit is not disturbed so as to maintain a constant potential gradient in the primary circuit. Then, now whatever thing is being balanced here, okay, there should be some potential source here, source of potential, and that when it is balanced, then the potential difference due to that Potential difference due to that across this balancing length should be same as the drop in potential across this potentiometer wire. So here potential difference across this must be same. So if I take potential difference as A and B, VAB, which is being balanced, then and if L is the balancing length, then I can write it is equal to the fall in potential per unit length, that is the potential gradient, multiplied by the balancing length. This is the principle of potentiometer in essence. Most of the problems revolve around this concept. Okay. Now we have to find the potential difference between this or between this. So that is same as the potential difference across the shunt, because it is given that it is shunted by some wire. So I can write I into shunt is the potential difference as per Ohm's law is equal to potential gradient into balancing length. Now this I will be EMF of the cell divided by total resistance. Total resistance will be the shunt resistance plus the internal resistance of the cell. So that means this is the formula which we'll be using here. Okay. So in the first case, the shunt is, you can check, the shunt is 5 ohm and the balancing length is 200 cm. So accordingly I can write one equation as E into 5 upon 5 plus R is equal to potential gradient multiplied by 200 centimeters. Similarly, in the second case, the shunt is 15 ohm and the balancing length is 300 cm. So for the second situation, I can write the equation as this: potential gradient multiplied by 300. So when we divide these two, we'll have 5 upon 5 plus R into 15 plus R upon 15 is equal to 2 by 3. Okay. So 3 5s of 15 gets cancelled here. So we are left with 15 plus R is equal to twice into 5 plus R. So R is equal to 5 ohm. Upon simplification, it will yield this result. So answer is 5 ohm. I hope that is clear. Then this was the last problem, students. That's all in this video. If you like my way of teaching, kindly subscribe to my channel and hit the like button. Thank you so much.